Welcome to our presentation. My name is Shintaro Narisada. This is a joint work with Yuki Matsumoto, Seira Hidano, Toshihiro Uchibayashi, Takuo Suganuma, Masahiro Hiji, and Shinsaku Kiyomoto. Recently, machine learning-based malware detectors are being used to detect unknown malware that cannot be detected by conventional pattern matching-based malware detectors. Typical training pipeline for machine learning-based malware detector is as follows. First, binary files of benign software and malware are collected by threat intelligence platforms through honeypot and sensors. Then, gathered binary files are labeled via dynamic and static analysis. For this binary dataset, a feature extraction algorithm is applied to extract feature vectors. These feature vectors plus their labels are usually used as training dataset for ML models. Finally, a malware classifier is constructed by learning the feature vectors. So far, a number of attacks against machine learning systems have been devised. These attacks are called adversarial machine learning. For malware classification domain, so-called backdoor attacks have been proposed in order to misclassify backdoor malware as goodware. There are two types of such backdoor attacks. Shen et al. Proposed poisoning attacks in the feature space. In the attacks, poisoning data are added to the training data in the feature space. Then a poisoned model is constructed. In the testing phase, the poisoned model misclassifies specific malware as goodware. On the other hand, Shibel et al. Proposed more realistic backdoor attacks in 2021. In the attacks, backdoor called a trigger is inserted into the input space, that is, binary files. This attack is more feasible than feature space attacks, since the TIPs often accept binary file submissions from users. In the testing phase, backdoor malware with the same trigger is misclassified as goodware. For feature space backdoor attacks, there are effective countermeasures. For instance, there are supervised anomaly detection methods that use clean training dataset for training. Madani et al. Use autoencoders as anomaly detectors for the training data. Samangoe et al. Applied GAN for anomaly detection during testing. For their methods, we note that Defender is assumed to have clean dataset for anomaly detectors. We will explain the countermeasures against input space backdoor attacks. For these attacks, unlike feature space attacks, a defender cannot assume the existence of clean training dataset. So, the training dataset for the model is contaminated. This is because the attacker inserts the poison during the data collection phase, and the defender cannot notice its presence. In existing research, major algorithms for unsupervised learning have been tried, such as spectral signatures, k-means clustering methods, and isolation forest. However, no effective countermeasures have been found against these attacks. This is our contribution. In our paper, we proposed fast effective countermeasures against input space backdoor attacks. Our countermeasure is based on autoencoder, not as anomaly detectors, but as surrogate data generator. Unlike normal autoencoders, our autoencoder does not require clean dataset. In practice, our autoencoder sanitizes backdoors for all Shibeli's backdoor algorithms and a stronger variant based on FGSM. From the table, our proposed method can drastically reduce the attack success rate for each backdoor algorithm's trigger size n and poisoning rate p. We will explain the series input space backdoor attacks briefly. We assume a stronger attacker with the following knowledge. Namely, she knows all of the feature extraction algorithm, structure of the prediction model, learning algorithm, and a part of the training dataset as attacker's dataset. So this is a white box attack. The attacker can submit backdoor binaries in the data accumulation phase. The sequence of input space backdoor attacks is as follows. First, the attacker determines the backdoor dimension and the backdoor value for the dimension in the feature space using the attacker's dataset and the surrogate model. They use sharp values for determining the backdoor dimensions and backdoor values in the feature space. Shibel et al. Proposed several algorithms to optimize the backdoor dimension and backdoor values for the dimension. In their paper, these algorithms are called feature selection algorithms and value selection algorithms, respectively. For more information about feature selection and value selection, please check our paper. Once backdoor dimensions and backdoor value are determined in the feature space, backdoor dimension and backdoor value are projected to the input space, exploiting the feature extraction algorithm. In order to know the relationship between the binary file and the feature vector, here the attacker must know the feature extraction algorithm. The attacker modifies the attacker's binary file so that the value of the backdoor dimension becomes the intended value in the feature space, and the other dimensions remain unchanged from the original value. Also, she has to keep the malware functionality, because if the binary stops working, there is no point in the backdoor attacks. Finally, generated backdoor instance is submitted to the TIP. After the poison model has been generated, misclassification occurs when backdoor malware is submitted into the poisoned model. For this attack scheme, our question is that whether the attacker can project all of the feature dimensions into the input space. If no, the input space backdoor attacks may have some limitations in this aspect, which can be applied for countermeasures. From now on, we will talk about our countermeasures against input space backdoor attacks. We first investigated the invertibility of the feature extraction algorithm. There are several feature extraction algorithms for binaries out there, but here we focused on the most common binary extractor, the EMBA extractor, which is also used in Shibari's paper. The EMBA extractor is a type of static extractor that takes a binary file as input and outputs 2351 dimensional feature vectors. We investigated the relationship between the 2351 dimensions in the feature space and the actual binaries. And we found that some dimensions are physically impossible to invert the backdoor while preserving binary functionality. The result is in the table. As you can see, there are 8 feature groups in the EMBA extractor. And for those features that use the statistical information of the entire binary, it is physically impossible to project the feature value back to the binary. We will show some examples for the EMBA extractor. For header file info group, 20 to 40 dimension correspond to the major OS version in the binary file. So if an attacker wants to set the value X in the feature space, she will overwrite the measure OS version with X in the binary file. For string extractor group, 2349 dimension means number of URLs in the binary file. In this case, the attacker can change the value of the feature space by adding or removing URLs in the actual binary file. However, for byte histogram group, 76 correspond to the occurrence rate of the string 4C in the entire binary file. It would be extremely difficult for an attacker to change the occurrence of 4C in the entire binary to the desired value without affecting the occurrence rate of other bytes or other features, and without destroying the functionality of the binary. This discussion is about the embedded dataset. But it is not the case for only the embedded set, as the same can be said about other domains where the input space and feature space are separated, such as extractors for Android malware and PDFs. If a defender can determine the potentially attackable dimensions in the feature space, we can consider some countermeasures for these attackable dimensions. We denote T as clean dataset consists of a feature vector and its label, and let A be an attacker's dataset. Dataset available for defender is a union of D and A. For irreversible vector S and invertible vector X, the feature vector V consists of S and X. For EMBA extractor, S is between 1 and 512 dimensions. A naive countermeasure for this situation is to cut off all attackable dimensions by dimensionality reduction. That is, we just set V equals S for all contaminated training data and inputs in the testing phase. This will, of course, get rid of the backdoor completely, but decrease the entire accuracy by trimming the important feature vectors, which may lead to detection error of backdoor malware. Another approach is to replace the vector X with surrogate data, aiming for a trade-off between the prediction accuracy and the attack success rate. We utilized autoencoders to generate the surrogate data. For contaminated dataset, we construct encoder and decoder so that the L2 distance of surrogate X and X are minimized. Normally, autoencoder is run to minimize the L2 distance of the entire feature vector. But here, we update the parameters so that the L2 distance of a part of the feature vector is minimized. Then, we replace all data in the contaminated dataset before training to the surrogate data and all inputs in testing phase. We expected our autoencoder achieves higher prediction accuracy than DR. However, there is a possibility that backdoor distribution will be learned. We will verify these points by our experiment and analysis. We want to avoid autoencoder from learning backdoor distribution. For small poisoning rate P, backdoor distribution can be considered as noise. We want to construct AE, not to run such minor distributions in the learning phase. To do so, we focused on the network structure and parameters of the AE. First, we set relative high compression rate for AE to exclude backdoor information from latent space of the AE. Second, we focused that large batch size is effective to reduce the attack success rate, since it can reduce the fraction of backdoors in a batch. Third, we applied batch normalization to AE to reduce the influence of backdoors on parameters of AE. we will show the performance of countermeasures against input space backdoor attacks. In our experiment, we used EMBER2 dataset, consists of 4,000 malware and goodware for training dataset, 1,000 malware for test dataset. We set the irreversible dimensions to be 1 to 512 as described, and the invertible dimensions to be the other dimensions. P-poisoning data with n backdoors in the invertible dimensions are generated by 3 backdoor generation algorithms as follows. In short, independent selection algorithm inserts backdoor in sparse and weak confidence area. Greedy combined selection inserts backdoor to be mixed in with the training data well. Additionally, we proposed FGSM-based label flip attacks that adds a backdoor to maximize contribution to goodware and flip the label. We set hyperparameters of AE as follows. First, we measured the prediction accuracy for clean models learned from clean training data or training data replaced by countermeasures. The table shows the results for proposed countermeasures. From the table, DR reduces the prediction accuracy by about 5%. As we expected, A achieved higher prediction accuracy than DR. Next, we measured the reduction in the attack success rate and prediction accuracy against the independent selection for each N and P. Compared to the original attack success rate shown in blue, A can reduce the attack success rate to almost the theoretical value of DR, while maintaining prediction accuracy, both when N is changed and when P is changed. Note that P equals 0 means adversarial example. We were surprised to see that even without poisoning, the attack was somewhat successful. This is the result for the greedy selection attack. This attack has been shown to be difficult to distinguish between clean data and backdoor data in previous results, since the backdoor points are well blended. However, our results show that A can also reduce the attack success rate for this attack. Chivalries to backdoor attacks are clean label attacks that don't perform any operations on the labels, because they were concerned with practicality. In order to evaluate the worst-case performance of our defense, we also implemented a more powerful backdoor attacks with label flipping called the FGSM-based attack. For this attack, A is still effective for small n and p, but protection performance drops as the poisoning rate grows. Finally, we conducted several analyses to verify that why AE generated from contaminated training data can reduce the attack success rate. First, we compare the sum of the absolute sharp value for clean training data and surrogate data by our AE. Our AE generates entire contaminated dataset with 1% poison. Left figure shows the sharp values for clean model and clean dataset. Purple lines show the backdoor dimension selected by the independent selection attack. As you can see, dimensions with high contribution to the prediction was chosen as backdoor dimension. Right figure shows sharp values for surrogate data from contaminated dataset. Note that 0 to 512 dimensions are not replaced. From the figure, the contribution of the backdoor dimension is actually reduced. We think that A seems to have ability to equalize the contribution for overall dimensions. Thus, incorrect contribution caused by the backdoor may be absorbed by the correct distributions. We also compared the data distribution for clean training data and surrogate training data. The upper figure shows the distribution of values in the original contaminated dataset, and the lower figure shows the distribution of the surrogate A. We note that almost dimensions of Ember dataset are based on categorical variables. In these dimensions, feature vectors consist of discrete values. Comparing the top and bottom, we can see that the occurrence of purple infrequent values have decreased in A. So A seems to ignore infrequent values from learning. In conclusion, we propose the first countermeasures against the input space backdoor attacks against ML-based malware classifier. We sanitize the backdoor for potentially attackable dimensions using the dimensionality reduction and the autoencoder as surrogate data generator. Especially, our A do not require the clean dataset. In our experiment, we showed that our A drastically reduced the attack success rate while returning the hierarchy. For future works, it will be interesting to make a concrete comparison to the existing non-supervised anomaly detection, or verifying the existing of adaptive backdoor attacks. Thank you very much for your attention.